So,
Yeah, I partied it up.
oh, somehow I don't see that as something you did last night. But perhaps you did. I don't know. I don't know your character that well. We're going to take a look at the solid cylinder. And for right now, I'm not going to draw that isometric view I attempted to and failed to draw yesterday. I'm going to draw a side view and a down the center view. So imagine that this is two angles of our solid cylinder. And our cylinder has, and I'm going to use the values that are in the problem that you have for my AP. We have a length L, and let's make it just a single value of R as the radius. And I want to emphasize that for the time being, L is actually to the size of R. So let's say that R is small compared to L. What this does and what this establishes is that we have a long cylinder. Not necessarily saying it's infinite, but this kind of statement is something we look for in these kinds of theoretical problems. This is to help us determine whether we can use Gauss's law as a means of solving for the interested idea. If they don't say that to you, then there might not be enough symmetry for you to successfully use Gauss's law. So a statement like this, or often they'll even exaggerate it a little bit by giving it the double less thans and greater thans, is a way of telling you that the object is big enough where it's infinite when you're inside of it, especially if you say you're going to be near the center. So they will also say, they'll just state without actually writing that down, that the object is very long compared to its width. Or they might just say it's a very long cylinder. You need to interpret that as being that you can treat it as infinitely long. If they ever say the word of finite length, that word finite, so if they say it's of finite length, they are trying to convey to you that you can't assume that it's infinite. And these aren't gray areas necessarily. Saying finite length is an indication completely that you cannot exploit the symmetry by assuming it's infinitely long. But if they in any way indicate that it's long compared to its other dimensions, then they are telling you that you could use the idea that it's of infinite length. So we're going to start the problem suggesting that our cylinder is of infinite length by saying that it is very long compared to its radius. Okay? So that's going to allow us to use a Gaussian surface to answer the question, which is, I want an expression for the electric field, a distance r from the center, inside the cylinder. And then, of course, we're going to extrapolate that to outside the cylinder as well. Let's say, for the argument's sake, that the cylinder has a total charge of Q. So we're going to start the process of using Gauss's law. And one of the first things I think you guys should do is figure out what is the volumetric charge density, since that's very likely to come up. What's an expression for the volumetric charge density? Do that part first. I'll give you a second or two, but I don't think it's particularly hard. For volume, we use rho. It's like a P, but without the hump. So I would draw a P like this, and I would just draw a rho in a single. All right, so that's what rho looks like for me. They're getting in a little argument here about if that's rho or if it's a P or what it is. It's rho. All right, so I would expect by now that you guys have an expression for the charge density that's something like Q over pi r squared L. And all you have to do is put the total charge over the total shape. And since we're talking about something that has volume, then that shape should be the volume of the object. Our next step and this is, I think, the easier one, is to figure out what kind of Gaussian surface we should use in order to try and figure out this electric field. And I hope that you guys have an idea in mind. Like, do you think a spherical shape would be appropriate here? No. I don't think it's going to have the right kind of symmetry. A squared shape? I don't think so either. What do you think the right kind of shape would be? I think a cylinder would probably work. So let's identify the center in here by placing kind of a line through the center. And I think we're talking about having a Gaussian surface that has itself centered. It doesn't have to be so long, but centered around my shape, like so. Does that look good? At the same time, we're talking about putting that same kind of shape here. So, down the center, that's kind of the size I'm going to look at. I'm going to make it have a radius of lowercase r. And let's go ahead and have let's call this h for the height of my cylinder. We doing good so far? Pretty straightforward? Let's start with building our expression for the flux. The electric flux has two parts: the area and the electric field, and then the comparison between the electric field direction and the area's direction. Now, just looking at this picture, I'm trying to remind you that we know the direction of the area for the top and bottom would be like that, and the direction of the area on the sides would be kind of in all directions, radial to the center. So, something like that. That good? So, the electric field. Do we have kind of an agreement that the electric field is very likely going to be parallel lines coming from the center? Kind of like so. Because if we have our agreement that that's how we think the electric field is going to be, then that allows us to take our flux and break it up into chunks. Places where we think we're going to have flux and places where we think we're not. So I can say we have E dot dA for the top plus E dot dA for the bottom plus E dot dA for the sides. Just like we did for the infinite line of charge. With the hope being that we can note that there is no flux to the top and bottom, because those two are going to have, the area is perpendicular to the direction of the electric field. But that's going to leave us with E dot dA on the sides. Now, I think we can also go one step further and evaluate this dot product to say that the cosine here has to be 0 degrees no matter where we are on the cylinder. Because if we're over here, the electric field is leaving and going through the cylinder this way. The electric field is also going to be in line with it in this direction. Both of those seem to make sense then, that we're going to have our electric field lined up with our area. So this lets me get rid of the dot product, but it also allows me to take this electric field and consider whether it's going to be of uniform size everywhere on that surface. Now we note that from our discussion before, when we talked about this a couple days ago with the sphere, I think it's not obvious. I think it bears discussion that the electric field here is only going to be based on the amount of charge that's inside the cylinder. I don't have to worry about the amount of charge on the outside of that cylinder. But at the same time, do we think that there's enough exploitable symmetry that we can say that the electric field is the same size as long as we are the same distance away from the center? Does that make reasonable sense? If it does, then we do get to exploit that symmetry. And then all we have to worry about then is finding an expression for the area of the side, which is 2 pi r h. And that becomes our expression for the flux. That the total flux is E times 2 pi r h. All right, so the other side of Gauss's law is Q enclosed. And this is why I needed to have the density, because we need to figure out how much charge is inside our Gaussian surface, which means we need to take the density and multiply by the volume of our Gaussian shape. But I really don't think that that's too tough. Would we all agree that the volume of our Gaussian shape is going to be pi little r squared times h? So if I substitute in the actual density, Q over pi big R squared L times pi little r squared h, I get to cancel out the pi's. And I get this kind of complex looking term. I'm putting the r's on the end of this because I think it's a point to bring up that there's this ratio of the little r to the big R. And it's the ratio of the squares. Well, we're at the end of this. Gauss's law is a comparison of the charge enclosed to the flux. So I think we can make that comparison now. I'm going to have my Q and then my H and then R squared over L capital R squared equals, don't forget my constant, epsilon naught, times E times 2 pi R H. So this allows me to get an expression now for the electric field. So first, I do realize H is going to go away. That was expected. One of the R's is going to cancel with one of the R's there. But then I really don't have anything else I can do. I'm just going to have to collect terms. I'm going to have QR in the numerator and a whole bunch of garbage here in the denominator. 2 pi epsilon naught, I like to collect those out front. And then LR squared. Questions at this point? First thing to point out, it's also linear. If I wanted to look at the electric field as I was moving from the center to the edge, it would be linear as I approach the edge of the cylinder. If this was a function of R. Of course, when this is all, as long as R is less than big R, when R is greater than big R, do you see that it probably collapses down to the electric field of a line of charge? That I'd have just that cylinder would just act like a line in the same way that the sphere acted like a point. So I'd get this. Oh, it's not r squared though. This is just r. So taper is a little bit less than a sphere because it's over r, but same idea. Now this is more what I would have liked to have assigned on the MyAP. The MyAP ramped up the difficulty level though, because in P you had part of a cylinder that was positively charged, and then part of the cylinder was negatively charged. So I don't remember all of the details, but I think I have most of them. So was the inside one was Q and the outside one was negative 2Q? Is that right? And then this radius was R, and this one was, I can't remember, 4R. So this is not drawn to scale. One of the, I won't say arguments, but one of the discussions that Abby and I had was, finding out the density of this section, the negative part. That was pretty hard. So I want to consider the two densities, the positive density and the negative density. To do so, we already know what the positive density is going to look like. Can you guys do me a favor, take a few minutes and perhaps put together what the negative density would look like? Like, how would you calculate what the negative charge density was of the blue part of the cylinder? I think that's a difficult conversation. So this part we already know. The positive one is just the total charge divided by the total volume. So if you want the negative one, you need the total charge divided by the total volume of the negative section. You guys are all here together. Figure out what the total volume of the negative section must be. That's not a physics question. It's a geometry question. So I'm going to pause for a minute. You have to take the bigger volume and subtract the smaller volume, is what it amounts to. And although the pi r squared L part doesn't change, you do have 4 squared minus 1 squared here. Because I'm seeing some confused faces out there, but do you need me to explain that more? Okay. So there's two volumes that we have to deal with. There's pi 4r squared L minus pi r squared L. This is the larger volume of the cylinder minus the part of the cylinder that's positively charged. So to get the shell, I got to take, the big radius and subtract out the small radius. And that's why it works out to be negative 2Q over 15 pi r squared L. That is the negative charge density. Now, again, having that is great, but you still have to be able to use that now, effectively in what you're going to do for your problem. You have to draw in a Gaussian surface that you can use to measure the electric field. And we just did this part that's inside the green. Doing the part that's outside the green and still in the blue, that's hard. Now, you don't actually have to change very much, but what you do have to do is recognize that your Q enclosed has to enclose both negative and positive charge. Now, when I've seen these problems in the past, they tend to be a little bit different in that they tend to have positive Q and negative Q, not positive Q and negative 2Q. The reason that's important to me is I want you to think about it. If the inside was positive Q and the outside was negative Q, when we get to the outside edge of the surface right here, the enclosed charge would be 0. Which means that there'd be no electric field outside this shape. On the other hand, what this does suggest is that we will eventually reach a point where our circle is wide enough where we will enclose, where we will enclose both positive charge and an equal amount of negative charge. I would suspect there's an R somewhere in the middle here where the electric field must be 0. I don't understand. Yes? Do whatever you want. Is that better? Sorry, I didn't realize I got bumped. Sorry. First world classroom problems. Now, I don't know where that is. I'm sure if I was writing the question, I would say, where is that? But it also suggests to me that whatever we get for our expression for the electric field probably has something being subtracted from something else, which would put us in a position where we could figure out the threshold value, the value for R for which the electric field would be 0. Now, this thought experiment we're having right now, I say we, I hope it's we and not just me. That's the kind of direction the AP exam is moving towards. Less about doing all of this and more about contemplating these kinds of places that must exist in a Gaussian surface like this. Now, I'm just going to go ahead and violate the copyright a bit, and I found a way to produce a nice PDF of the problem, and I will post it back up there for those of you who hadn't had a chance to take a look at it. Although it's supposed to be due today, I'll give it to the following Monday so you guys can kind of bang it around this weekend, okay? And you guys who need to submit it because you couldn't submit it online or want to take another look at it, I hope this has set you up enough where you should be able to work through the question. It's still not easy. There's a lot here mathematically that's tough, but I think you should have enough to get you through. And I want to see your answers on Monday, please. You guys good at home? All right, you guys
So are we
good here?
submitting this on are we submitting this on Canvas or my AP?
I will have a submission button on Canvas for you guys if you've already submitted on my AP but want to take another look at it. All right?
All right.
Bye, guys.
Good.
Have a good weekend.
Have a great day.